Symmetric to the y-axis. In my head, what do I think? Opposite of y is? Opposite of x is? I'm going to plug in negative x. I swear that's what I think. So here we go. I'm plugging in negative x. So negative x times y is equal to negative 6. I want it to look like the function above. What do I mathematically have to do to this to even see if it's going to look like it? Divide by negative 1. Okay? Which will cancel that out, and I get xy is equal to positive 6. Is that going to work? Okay. No. Nope. All right. Let's try. Symmetric to, let's go x-axis, which means opposite of x is, and opposite of y is, so I'm going to plug in negative y. What's going to happen here? Same thing. Same thing's going to happen. Ain't no darn thing. Nothing. Nope. Now what do? Check origin. Symmetry to origin. What do I do on this one? I have to plug them both. So I've got negative x, negative y is equal to negative 6. What's negative times negative? Positive. Positive. Uh-oh. Does it match? Yes. The original function? Yes. So does this thing have symmetry? Yes. Yes, it is symmetric to the, so it's symmetric to the origin, which means, is it an even, odd, or neither function? Odd function. How do you know? The O's. Me too. I know it that way too. They both start with O's. Okay? How many of you had that correct? Okay. If you did not, tell me questions, or do you know why you didn't have that? Anybody? Thoughts? Which one?
The origin, did you divide it? Or?
No, a negative times a negative is a positive. Okay? Any other questions? So let's try this one. I don't know what example 3 is going to be. Try it. Okay. Check the symmetry on that. 2 over x squared. See what it's going to be. What do I plug in? And I'm checking symmetry to the y-axis for me. Negative x. Here we go. Y is equal to 2 over negative x squared. What is negative x times negative x? Positive x. Does that match the original function? Yeah, that's good. All right, let's check symmetry to the x-axis. What do I plug in? Negative y. Negative y is equal to 2 over x squared. What do I need to do to both sides? Divide by negative 1. All right, now think. Divide everything by negative 1. Negative divided by negative is a positive. What is anything positive divided by negative 1? Negative that thing, right? Is that the original? Nope. And then check the origin just for kicks. Move over here so I can get out of your way. There's no writing. Origin, I have to put in negative x and negative y, right? So negative y is equal to 2 over negative x squared. Negative x squared is negative x times negative x, which is positive. And now what am I going to do? Divide by negative 1, and dang it if it's not the same thing we had with the x-axis, isn't it? Is it going to work out? No. So, symmetric to the origin? No. That should be an N. It is symmetric to the y-axis. Move that up. Which means If it is symmetric to the y-axis, what kind of a function? Even. Excuse me. Questions? Parker, you good? Yeah? Brandy, good? Any questions at all? How many of you have even symmetry to the y-axis? Questions at all? Alicia, you're all right? Yeah?
Can there be two of them?
It can be. It can be. What a nice segue. Let me just hold that thought. I want you to ask that question here in just a second. Folks, I want you to write down this next equation. I want you to see what happens. If there can be more than one type of symmetry, can we have an equation that doesn't have any symmetry at all? Ding, 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 ding. Example 4. Okay. You already know this is going to be what type of an example? This is going to be a no symmetry example. I promise. But we are going to prove it. Okay? We're going to prove it. We have to do the very same thing we did earlier. Check the y-axis, check the x-axis, check the origin. Okay? We're going to do this one together. All right, symmetric to the y-axis, what am I plugging in? Negative x. All right, so y is equal to negative 2 times negative x cubed plus 7 times negative x minus 2. Y'all agree? Everybody cool? All right, what is negative 2 times, what's negative x times negative x? Positive x. What's positive x times negative x? Negative x cubed, right? What's 7 times negative x? Negative 7x. Do I need to go any farther with this? Is that going to match the original function? Why? Because it's negative 7x. That right there is why it's not going to be symmetric. That negative 7x, it has to be plus 7x. Is everybody cool? So it's not symmetric to the y-axis. Let's check symmetry to the x-axis. All right, this over here. I'm plugging in what, y'all? Negative y. So negative y is equal to negative 2x cubed plus 7x minus 2. What do I do? Divide by negative 1. And what we do, one thing, we have to do the error thing. Negative divided by a negative is a positive. A negative divided by a negative is a positive, right? Okay. A positive divided by a negative is a... Oh, what? Immediately. Nope. Can I stop right there? Yep. I can. I don't have to go any farther. Why? Because I have a positive 2x cubed, which is totally different than the beginning, and I have a negative 7x. So this is a big old, move to the next one. This is a big old no on this one. Folks, if it's not symmetric to the x-axis and it's not symmetric to the y-axis, do I need to check the origin? Let's just check it for kicks and giggles. So here we go. We're plugging in everything's negative, right? So we've got negative y is equal to negative 2 times negative x cubed plus 7 times negative x minus 2. Everybody cool? You know what I'm doing? Okay, good. Wow. Negative y. We'll simplify all of our x terms. What is negative x to the third power going to end up being? A positive or a negative? What is negative 2 times negative x cubed? What did I just say? I did say positive 2. So a negative times a negative is a... Give me your hand. I like to whoop your... A negative times a negative is a... Right? Okay. Positive 2x cubed. What's positive 7 times negative x? Negative 7x minus 2. Is that right? Was that the original? No. So what? What's that mean? It didn't work for any of them. What's that mean, y'all? No, did I make a mistake? No, I didn't make a mistake. There is no symmetry. No symmetry. Is that acceptable? Yeah, that's acceptable, but you're just describing the graph, that's all. But this is how you would prove the symmetry algebraically. Because I don't have a picture of it, okay? Now, ask your question again. Somebody asked that question a while ago, and I said, hold that question. Can there be more than one? Can functions have all three types of symmetry? Yes, they can. But that's not the one I want to go over. I want to do this one. Can functions have no symmetry, yes or no? Yes, we just did one, right? Write this down. Can functions have no symmetry? Yes. Absolutely. And I don't care if you write this in this manner, you know, with a chart. I don't care if you do that or not, just it makes it easy for me. If a function is not symmetrical, if it's not symmetrical, then couldn't it look like this? I mean, is that symmetrical? No. No. Is this symmetrical? That just looks weird. Let's just go there. Is that symmetrical? No, that's not symmetrical. Okay? It could be a polynomial function. This would be a cubic function, probably. Natalie, do you remember what this one is?
Not really.
Kayla, do you remember what that might be? Here's just a little precursor for about 2 weeks from now. Count. 1, 2, 3, 4, 5, 6. Do y'all see that? 1, 2, 3, 4, 5, 6. Do you see? This one could be an x to the 6th polynomial. There's no symmetry in that. Holy crap. It's got all kinds of x-intercepts, got some y-intercepts going on. That's crazy stuff. But does it have symmetry? No. No symmetry on that one. Then my question, can they have all three types? Yes. They can. Write this down. They can have all types of symmetry. You're making me kind of nervous. Think what kind of function, what kind of picture would have all kinds of symmetry? All. A circle would. That's exactly right. A circle would have, and that is a sucky circle, okay? The way I have it drawn, there is no symmetry at all because number one, it is not circular. Number two, its center is not the origin of the Cartesian plane. But do you remember what a circle equation looks like? Does anybody remember? You would have learned it. Yeah, y'all would have learned it in geometry because you've been through the new geometry SOLs. It might look something like this: x squared plus y squared equals 25. But here's my problem with that. Is a circle a function? Why not? It will not pass the vertical line test, right? Kind of weird to say what function and it's not a function. Here's something else, something that we may not get to. We may or may not. We probably won't. I don't ever get to it. But if it were a perfect oval, folks, this is an ellipse. Just so you know, we got a circle up here. And of course, my ellipse is not very elliptical. It's kind of heavy on the right side, don't you think? It is. It's a second picture. I claim that. But it would look like this: x squared plus 4y squared equals 16. That's an ellipse. And there's one other one that would have all symmetry. See if I can draw this better. Does anybody know? That's still not symmetrical. Don't judge it. What is it? No. No. Does anybody know what that is? If you've not gone over conic sections, which you guys had to identify conics. Don't you have to identify conic sections in Algebra 2? No. No. Okay, great. I learned so much more in Algebra 2 than y'all do now because of the stupid SOLs. I hate those things. Did I get that on? Yes, good. It's video. I hate them. It's you. Shut up. This is called hyperbola. It is not a hyperbola. It is not a disease that you get in math class. Okay? It's a hyperbola. And it would be something like this. 95x squared minus 25y squared equals 1. Just in case you're ever on Jeopardy and you need to know that, or Quiz Bowl team. There you go. Okay? So, when we're finding, let's recap, when you are finding x-intercepts, how do you do that algebraically? Plug in 0 for y and solve. When you are solving, that's x-intercepts. I better write it down because I'll forget. When you are solving for the y-intercepts, what do? Plug in 0 for x and solve. When you are testing symmetry to the y-axis, what do you plug in, everybody? Negative x. So we want to get always back to the original. When we are testing symmetry to the x-axis, we plug in negative y, get to the original function. And if we're checking symmetry to the origin, we plug in negative x and negative y, right? Facile or difficile? Facile? Good. All right. Let's move on. Let's change gears a little bit. On drawing the graphs, okay? But do you know that a continuous function is not going to have any holes, no breaks, no gaps? Do you know that? You know that from last year, Algebra 2. Yes, no, or maybe? If you say, throw your hand up. You got it. Go up high. How many of you are like, maybe it's like riding a bike, I'll remember when you tell me? Okay. Okay. All right, maybe. So, I don't think, you know anything about this continuity. I don't think. Well, let me show you something. You will have the ability, I love on this, to put that where it goes. You don't know what it is. Where do you think these words go? Infinite discontinuity, removable discontinuity, and jump discontinuity. There are 3 types that we're going to talk about. You got to figure out where they go. Who's got it? Come on, be bold. Go, Matt.
She's already taken it.
She is voluntary. Okay, so you have a second. But boom. Okay? You can only do one of them. All right, who's got the next one? Go, Brandon. Come on. It's all right if you get it wrong. Why? It's okay to get it wrong now. Infinite. What do you think, Heather? If you think anything needs to be corrected, correct it. What's infinite mean? Say it again, I'm sorry. Goes on forever. Do those look like it would be right? We'll choose context clues. I used to love context clues when I was little in elementary school. Did y'all learn about context clues? Do you learn about them now while you're reading Jungle? Haley's favorite book. Okay. Why do you think removable discontinuity might be in the right place?
Because it's removed in that hole.
Shut your face. Something has been removed from that function, right? Okay. Why would infinite discontinuity be the one in the middle?
They never touch
It never touches what?
the asymptote.
What kind of asymptote? Vertical asymptote. And that function appears to be going into positive infinity and negative infinity, right? So infinite discontinuity, it's all right.
He can afford some more of his own.
Oh, okay.
Guys, you guys, you know you had Miss Mabry's elementary teacher? You did? Did you really?
So you said jump from one line to another, yes? Do you think they're in the right place? Right it above those pictures, because they are in the right places. You guys did really well because you chose correctly, you chose wisely. And you kind of do have to use context clues, okay? So what's next? I don't know if it goes down the slide or across. So maybe it's going across. Looks like example 1 is across there. Let's check it out. Check it out. Check it out.
You saved yourself.
She doesn't. They don't know that.
Already said. I cannot. All right, check this out though. I do want you to make a few little notes because it will make sense when we jump on example 1. You said something was removed, right?
Yes.
It has a point where it's not defined, and we know it's not defined because of the open circle. That was priceless. We have a vertical asymptote. Do you know what kind of function you deal with when you have a vertical asymptote? Anybody remember? It is a rational function. Now, I'm still just like, what? What does a rational function look like? No, tell me what the equation actually looks like. What's a rational function look like?
You have an X in the bottom of the function.
It's a fraction. It's a function that is a fraction. Okay? And then that jump discontinuity, do you know what that's going to look like? Does that look like anything that we dealt with earlier in this class?
Yes.
What kind of function? Come on, come on, come on. What? Yes, it's a piecewise function. Okay? I still feel like I just need to do this all day. I just need to keep it up all day. All right, piecewise. Oh, Lord have mercy. Wow. Oh, my God. Let's look at example 1. I'm just going to grin all day long.
You should play the Kevin Hogan. That was fun.
Well, I didn't look. It's all right.
You should watch them before you show them the class.
I should do that. But shouldn't I? Don't you think I know to do that? Yes, I know to do that. Do I ever think to do that? I just take my chances. Clearly. You gotta thank you.
I wonder if Mr. Gibbs know what the anaconda is.
What would it look like on the graph itself? If it's continuous, what's it gonna look like? Pardon me?
It can be a line number.
There'll be a solid piece of the line, right? If it's discontinuous, then there will be a hole, a gap, or a jump. Do you guys agree with that? So there will be a solid piece of the line. Now, here's what I want you to pay attention to, if I can find it. How are we going to determine if there's going to be a solid piece on the curve when x is equal to 1/2. You're saying if there's a picture, I don't know what the picture looks like, but if there's a picture and this is 1/2, then it better be it better be a value there, right? So how am I going to determine if it is continuous when x is equal to 1/2? What does it also have to have? What? It has to have a y value. Well, how am I going to know if it has a y value? No, easier than that. Way easier than that. You said it's got to have an x, got to have a y, right? Well, I got the x. How can I find the y? Plug it in. What is f of x, y'all? It's really just y. So I'm going to rewrite f of 1/2, right, as 2/1 times 1/2 plus 1. Is that okay? What's 2 times 1/2? 1. What do I get? What's that mean? Is it continuous at x equals 1/2?
Yeah. Where did 2/1 come from?
2. I rewrote this 2 as 2/1 because that's what it is. Anytime I have a fraction, I want to make everything around it a fraction if I'm multiplying or adding. Is that continuous, yes or no? Yes, it is continuous. Bless you. Continuous when x equals 1/2. How do I know? Because I get a valid y value. My ordered pair is 1/2, 1/2. If I had to plot a point on that curve when x is 1/2, its corresponding y value happens to be the same thing. Is it always going to be the same number? No. But for this function, it just happens to be y equals 1/2. Okay? Questions at all? So when I'm figuring out whether it's continuous at a particular x value, all I want to do is what? Plug it into the function and see if I get a y value. Okay? Does that make sense? Yes or no? Let's see what happens with the next one. So see if f of x, which is equal to 1/x minus 1, see if it is continuous or discontinuous when x equals 1. See what you get there. Say it again. 1/x. What am I going to do with that 1 over there? I'm going to plug it in f of 1. I'm going to plug it in where I see an x, right? So I get 1/0. It's undefined. When 0 is under the fraction bar, it's undefined, right? Okay? So it is undefined. So what's that mean? It means that it's discontinuous. At x equals 1. Folks, this right here, I know you're thinking, why should I have no start on this out? Because when you get to calculus next year, it is never again about writing x is 1/2 and you're done with it. You have to, it's a whole lot more to it. You got to write out things in sentence form or in phrase form in calculus, okay? But it is discontinuous at x equals 1. Does anybody know what kind of discontinuity it is? It's a fraction as a function. It's a what? It's infinite discontinuity. Do you know why? Because I have 0 at the bottom. Well, it's infinite because it is a rational function. with a vertical asymptote. It is infinite discontinuity because it's a rational function, it's a fraction with a vertical asymptote. How do I know it has a vertical asymptote?
Because all rational functions do. It isn't touchable.
It doesn't touch that function, it doesn't touch x equals 1. There's a dotted line there, okay? Can we move on to the next one? What's the next one? Flip it over. I don't even know. Oh, yeah. All right. This is good stuff. I happened upon this last semester. It is the best discontinuity information I have ever found. I didn't make it up. I just stole it from something. I don't even know where. But it is some good information. Look, you've got two types of discontinuities. You've got removable and you've got non-removable. Well, okay, big deal. Removable is point discontinuity, which is, we called it removable. All right, do you remember what picture that was? It was the very first one. Describe that graph. It had a hole in it. Okay, let's draw a parabola with a hole in it. Hole in curve. Because that's what it is, right? Oh, and it's right there below it anyway. What do you look for when it's infinite discontinuity? The vertical asymptote. Okay? Has a vertical asymptote. How do you know the graph has an asymptote? What do we look for in the drawing? The dotted line, the vertical dotted line. And what's the graph look like if it's jump discontinuity? Pardon me? Kind of jumps from one piece to another. What kind of function though is it? It's piecewise function. Okay. The description of the graph, it has a jumps to a second piece, if you will. And you need to put that it's a piecewise function. 99% of the time, if it's a piecewise function, it has jump discontinuity. 99% of the time. But what about that other 1% of the time? It may just have something called point. Okay? And I'll show you that here in just a second. Check that out. Check the pictures below. The graph below has a removable discontinuity at x equals 1. Do you guys agree with that? Yeah? What was the domain? Write the domain in the range of that first picture for me. In there. In that first one.
I think I got it wrong, but I put parentheses, negative infinity, 1, and then parentheses, union, 1, negative infinity. No, positive infinity.
Positive infinity, right. How many of you had that? That's perfect. Perfect. Good. Everybody have domain? What's the range? Tyler, what's range?
Okay.
How do you know? Because what? Because the arrows. All right, now let me ask you this, because this is always a question, but it's got a hole in it.
No, I don't want to start it.
But it's a solid right there. And what did I tell you? Once included, always included, right? So even though this point right here is included, I just keep on getting it. So it is all reals or negative infinity to positive infinity, right? Okay? Hannah, what'd you get for the next one? What'd you get for the domain?
I haven't got it.
Okay, what would you get for the domain?
Negative infinity. 1
agree? Yeah? Yep. It's not, never gonna be defined at the vertical asymptote when x is 1, right? So it's never gonna be defined. This right here, the 1 parentheses union parentheses 1, what is it really representing, the vertical asymptote? So I have to account for it because it is going to get all the way close, just as close as it can get. But it's never going to include x equals 1. Okay? So what would the range be then? What would the range be? Denisha, what would the range be for that one?
Would be parentheses negative infinity. That'd be like 4.5.
No, negative infinity means it's going to keep going down, right? Okay? So it's all the way down here. But what about up here?
30.
Positive infinity, isn't it all reals? Y'all? How many of you say yeah, all reals? Do you understand? Yes? No, or maybe? Kat, what about the next one? What would the domain be? But what about that whole there? I'm not questioning you. I want you to be 100% certain. I'm not saying you're wrong. I'm just asking. It's got a hole there, and that's what it usually trips everybody up. But it's included up here, so I don't flinch. When I'm checking it from left to right, I don't flinch when I see that. Know why? Once included, always included. So do you guys agree with Kat, all reals? Yeah? Joe, what about the range?
Parentheses negative infinity for negative infinity for parentheses union for negative positive infinity.
What about 4 though? What do you think? Okay. What is range? What do I look at for range? Bottom to top. What's the bottom most? Joe, you just got it, didn't you? Joe, what did you? Because this was your face. Joe was looking at it and he went. Joe, what'd you make the face for? You're not sure. Hey, Haley, what about it? What's the bottom most y value on this graph?
What?
What's the bottom? Okay, Haley. What's the bottom most y value on this graph? How come? Because that arrow. Absolutely. It has an arrow. It's all the way down here, isn't it? So negative infinity, absolutely, I agree with you, 150%. What's the highest y value going to be? I'm here, working my way up. Uh-oh, there's a circle. Do I flinch? Why? Because it's included over here. Don't flinch. Want to keep going. I move up here, and I get here, and oh, what's going to happen? What's going to happen when I get up here to y is 4? Oh, God. It keeps going. Don't flinch. It's just over here somewhere, isn't it? Is it included? Yeah, it's included. Then what happens? It keeps going forever, ever. So what's the range, y'all? All reals. It is all reals. What do you think? Could you do that on your own? You're going to have to. You got to. Got to be able to do that. Okay? Is discontinuous. All right? So, where does it have removable discontinuity? Where does it have jump discontinuity? And where does it have infinite discontinuity? Removable,
4.
pardon me, for which one? For removable? How come? What was the clue? What was your visual cue? The circle. There's a piece of the function that's been removed. It's like it took a hole puncher, didn't it? Like it's been punched out of there. How about jump discontinuity? I don't know. The non-removable, I don't like that. Just put jump. Where does it have jump discontinuity?
-1.
And who?
-1.
I don't think Y. I gotta think X values.
-1.
No, I gotta think X values. When X is equal to,
-1.
there we go. I didn't hear it. Oh. Okay. At X equals -1, we have where it jumped from the open circle when Y was 1 down to the closed circle when Y was -6, right? And then I guess it has infinite discontinuity when or at X equals what? What do you think? Facile, difficile. Very, very facile. Holy, easy. Right? So here's what you need to do. I'll show you that. I'll show that to you later. Flip that over. Okay, this is what I want you to do. You see this page right here? Okay, you got these 3 problems that you have to do for homework, and look what it's covering. I want you to name all of the discontinuities, because all 3 of these pictures have more than one type of discontinuity. If you were to have, let's just say, what kind of discontinuity does it have right here when X is 0? Okay, so you're going to put removable disc at X equals 0. And then, what's the other one? Jump disc at X equals what, y'all? C. And then you got domain and range. I know. So you've got 3 dirties. Holy help me. These 3 problems for homework. Okay? All 3 of these. These 3 examples of discontinuity and domain and range. We'll go back and pick up all the rest of the stuff on Wednesday, because that would be a good review for us. Then I want you to turn to page 21. Through 58. And it's just domain and range. Just domain and range, okay? Believe it or not. Oh, and little something. Oh yeah, here it is. Check out this DQ that's really not a DQ. Okay? Still recording, yes. I want you to find the domain of 1, 2, and 3 using algebra only, no pictures. If you don't show your work, you're not getting credit for it. Okay? I know, I'm hateful, don't care. Number 4, more domain and range, you're welcome. Guys, this is going to be for a grade. And it is due on Wednesday. Okay? Next Wednesday. Holy moly, that's a long time. But look at number 4 real quickly. The picture ought to look like this. Oh. It's going to look something like that. You may need to draw in the X and the Y axes because you can't really see it on some of them. Some of them you can't, like this one I can see it, some of them you can't. But this is the -6, 0. This is your 0, 4. This is your 2, 0. And this is your 5, 0. I might draw in the X and Y axis just so I can see it. Enjoy your time. Have a good day.